Hello to all dears. Again, we can continue the contents of topological groups. In the previous session, we see the definition of topological space and open sets, closed sets. Now, in this definition, we see the definition of closure. Let X and tau be a topological space, so that tau is a topology on X. You know that a topology have three properties, okay? Empty set and X must belong to tau, and for each subset of tau such as U, its union must be belong to tau, and for each two element in tau, its intersection must be belong to tau, okay? So this X and tau is a topological space, and tau is a topology on X. And S is a subset of X. Then the closure of S, denoted by S bar, is defined to be this set, the intersection of all closed set such as F, such that F is a subset of X contains S. Okay? All closed subset of X that contains S. So that sorry, in this remark that I expressed for you in the previous session, I have a mistake in this line. F alpha is closed so that its complement is open, and so that by B this set is open, because all of this is open, okay? Mr. Muhammad Hassan and one other student mentioned this mistake to me, and we must correct this. This is closed, okay? This is open because F alpha is closed so that its complement is open. Thank you, Muhammad Hassan. And one of other students is open, okay? Open. So that this union is open too, okay? Now, okay, I'm Mr. Amir. Thank you, Muhammad Hassan. Thank you very much. But in this new definitions, let X and tau be a topological space, and S is a subset of X, not necessarily in tau, okay? Then the closure of S defined by this, the intersection of F such that F is a closed subset of X and S is a subset of F, so that this F has two properties. F is closed and F contains S, okay? Contains S. Or the intersection of these sets. F is a closed subset of X and S is a subset of F, okay? This intersection define the closure of S bar, okay? So that since all of these F are closed, this intersection is closed by our previous remark. We see that any intersection of closed set is a closed set, okay? So that S bar is always closed. Whenever is closed or not, it is not important, but we have this proposition or remark for each subset of X. S bar is always closed, okay? Closed, okay. And in symbols, the closure can be written as this: S bar equal to the set of all X such that the intersection of N and S is non-empty for all N in N of X, for all N. It isn't obvious that these two sets are the same. A proof of this is given in 1. Intuitively, we can think of S bar as the smallest closed set that contains S. It is not that I write this for you. S bar is closed because S bar is a intersection of closed sets, okay? S bar is closed, and so it is trivial that S bar is contains S, because all of these contain S, all of this F, so that its intersection must be contain S2. Okay, all of these contain S, so that its intersection contain S. And 3, if, for example, F is closed and contain S, then S bar is a subset of F. And this is trivial because if F is closed and contain F, this F is a F such as this, is a member of this set, and this intersection is less than all of these elements. Okay, so that S bar is a subset of F. The intersection of this family is smaller than all of these elements. Okay, the intersection of this family is smaller than each element of this family. Okay, so that if we have F is closed and contain F, F is a member of this family, so that S bar is less than this F. So that these three properties say that S bar is closed, contains S, and a smaller closed set that contains S, that we see in this. S bar is the smallest closed set that contains S. And also we have this equality. We have this equality that its proof is not difficult. You can prove this. Okay, please prove this equality as a practice or exercise. Okay, it is not difficult for you. I recall that n of x that defined in this page, end of this page. The set of all neighborhoods of an element x will be denoted by n indexed by x. Okay, nx, the set of all neighborhoods, and a set n of x is a neighborhood of x if there exists some element of 2 such as u with this property: x belongs to u and u is a subset of n. Okay, so that we can use this or this as the definition of the closure of a set S. Please note that if we consider this set, okay, let we define this by S tilde, okay, the set of all x in x such that for all n in nx, this intersection not equal empty set. This is a set that we can define the set of all x such that for all n in n of x, the intersection of n and s is non-empty, such as this set that defined in the book. Then we see that if n belong to this and this intersection equal to empty set, then S must be contained in this complement, okay? Okay? So that if we consider this n, for example, and this S, if this n and S are disjoint, then S is a subset of the complement of n, and this is the complement of n, for example, that must be contained whole of S, okay, whole of S. And we know that this is a closed set because n is open, n is open. Not open, but contain, by this definition, contain an open set, okay? Contains an open set. So that we can write by this. There exists one u into such that x belong to u and u is a subset of n by the definition of neighborhood, so that we can see that okay, from this and this. x minus n is a subset x minus u. Okay, and this is closed because u is open, and by this two relation, S is a subset of this closed set, so that this is one F subset that we use in the definition of the closure of S. Okay, and so that since S bar is the smallest closed set by this property, S bar is a subset of this set. And since X is an element in U, so that X not belong to this, so that X not belong to S bar. Okay, so that by this process we see that if X not belong to this set, then we have this, and finally X not belong to S bar, because if X not belong to S bar, we have there exists, okay, there exists one n by this property. Please note that. Please note that X belong to, I use another clause, X belong to S tilde equal to, for each n in n of X, this intersection must be non-empty, so that if X not belong to S tilde, then there exists, or we can write equivalent, the negation of this property, X belong to S tilde, and this is equal to negation of this quantity, and the negation of this equal to there exists one element of n of X such as n, such that this intersection be empty set. Okay, So that by this property, if x not belong to S bar, there exists one n by this property, so that we have this and we have this, so that x not belong to S bar, so that we prove this, that x not belong to S bar implies that x not belong to S bar, and this is equal to x belong to S bar, then x belong to S tilde. This is hold by these properties that we know. This implication is equal to this implication. Okay, this implication equal to this, and this is equal to that S bar is a subset of S tilde. And similarly, you can prove the inverse of this relation. Okay, you can prove the inverse of this relation, so that we have this equality, that S tilde equal to S bar. Okay, dear students, do you have my voice and image? Do you have my voice and image? Okay, thank you very much. And so you can use this definition or this for the closure of S. And we have the definition of dense subset. Let X and tau be a topological space. We say that a set D is dense in S whenever the closure of D be equal to whole of X. This closure equal to whole of X. Then we say that D is dense in X. Example, Q is dense in R real numbers with the Euclidean topology. Okay, because you know that okay, example, Q rational number is dense. The rational number is dense in Euclidean topology. Okay, in R with Euclidean topology that I mentioned to you. For this, we must prove that the closure of Q equal to whole of R. This is a trivial relation that we have. Q bar is a subset of real numbers. Sorry, let me a minute. آقای محمدی سلام قربانت، من سر کلاس هستم، ببخشید نشد. قربان شما جان میدارم. خدا. Sorry. So we must prove this relation for this equality, so that you can set an element of R such as X and see that this X is in the closure of rational number, but it is trivial because if X belongs to R, then for each n there exists n intervals such as A and B, such that X belongs to this interval and this interval be a subset of n. Okay, by this definition of neighborhood, X belongs to one open set. In Euclidean, you can choose this open set as an open interval. Okay, as open interval. Now we see that this interval intersect by rational number is a subset of this intersection by this relation. Okay, but we know that this is empty set, so that this is empty set. Okay, this is empty set, and we can write this intersection is non-empty, or we can say this by 1, this hold by 1, that this is a non-empty set because this set is non-empty and this is a subset of, and this is very easy. You know that between each two distinct elements such as A and B, okay, such as A and B. There exists one rational number, and between each two distinct real numbers there exists an infinite rational number, because we can find a rational number in this interval, in this interval, in this interval, so that we have infinite rational number in these intervals, and so that this intersection is non-empty, so that this is non-empty. For each n, this is non-empty, so that this shows that this property full of this shows that X is an element in the closure of Q, so that by this line we see that we have this implication, and R is a subset of this closure, and we have this always, so that this is true. This line shows that R is a subset of the closure of Q. Okay, do you understand this proof, dear students? Okay, thank you Amir, thank you Abdul Jabbar, Ali Akbar. Okay, thank you very much, it's very good. So that we have this example, Q is dense in R with Euclidean topology, and the definition of base, let X and tau be a topological space. A base beta for tau is a subset of tau, where each open set in tau can be written as a union of elements in beta. Okay, so that we can write this definition. Let X of tau be a topological space and S is a subset of tau. Then S is a base for tau. Okay, base for tau. If and only if for each u into, there exists a family such as A alpha, for example, in S such that U equal to this union. Okay? For each U, there exists a family in S such that U is the union of the element of this family. Please pay attention. A base beta, for example, I write S. For tau is a subset of tau where each open set into any element into can be written as a union of element in beta. A union. I write this union by this. Okay? And in the book write this by bit B. Okay? We can write this. Or any letter, it is not important, but I like use symbol similar to book. Okay? Beta is a base if and only if each element of tau can be written as a union of S members or beta members. A union of beta members. Okay? And definition, let X and tau be a topological space. A subbase for tau is a set such as this with the property that the set of all finite intersection of sets in this family is a base for tau. Okay? For example, if we consider we can write this definition. A subset, for example, if of tau is called a subbase for tau, whenever the set beta equal to finite intersection n is a natural number and a1 up to an belong to f. Be a base for 2. Okay? A subbase such as f is a subset of 2 such that if we construct all finite intersections of element in F, then this set be a base, or any element of 2 can be written as a union of this element. Okay, this is the definition of base. Okay, any element of 2 can be written as a union of beta elements. Now for subbase, at first we can construct beta, the set of all finite intersection of element in F. Then this beta must be a base for 2. Okay, let X and 2 be a topological space. A subbase for 2 is a set such as F of 2 with the property that the set of all finite intersections of sets in F is a base for 2. Okay. Example, let X and 2 be a topological space with X equal to the cube of R to the power of 3, and 2 is a Euclidean topology in R3. The set of all open box is a base for this topology, since any open set can be written as a union of open box. Please note that in Euclidean topology, in the case n equal to 1, this is a base. Okay, because we know that any open set in Euclidean topology can be written as a union of open intervals. Okay, by the definition of Euclidean topology, there exists a family of open intervals such that U equal to this union. Okay, and we know that this family can be considered as a countable family, okay? And in the case n equal to, this is a base, the set of all for example this product of interval such that these are real numbers, and in the case n equal to 3, this is a base the product of n open interval in general case, and in n equal to 3 we can write completely, okay? In general case we can go back n open interval, okay? This is a base for Euclidean topology on R. This is the base for Euclidean topology in R2, and this is the base for Euclidean topology in R3, okay? In this case, any open set is a union of this square, and in n equal 3 any open set can be written as a union of these cubes, and in n equal to 1 we can consider open intervals, okay? Open interval. And a subbase for tau Euclidean topology is the set of all open boxes with volume less than volume greater or equal 1, greater or equal 1. This is a subbase for tau since any open box can be written as a finite intersection of element in the subbase, because any of these box or cubes can be written by a finite intersection of cube but volume greater or equal 1, because it is trivial that we can intersect two cube with volume greater than 1, such as these two, okay? Such as these two. And obtain a smaller, the intersection of these two is a cube again, okay, but by a smaller volume, okay, so that by finite intersection of cube but this property volume greater or equal 1, we can construct all cubes and all boxes so that we can construct a base, okay, we can reach to a base by consider finite intersection of box with volume greater or equal 1, so that the set of all box with volume greater or equal 1 is a base for Euclidean topology, for example, okay. And we have this. Dear students, do you have my voice and do you see this PowerPoint? Do you can see my PowerPoint and do you have my voice? Okay, thank you. Thank you very much. Thank you. A fundamental system of neighborhoods can be thought of as localizing the notion of a base. In fact, a local base, okay, around a single point. By this definition, let X and 2 be a topological space. Let X be an element in X and let UX be the set of all open neighborhoods of X. The set of all open neighborhoods, not all neighborhoods that we denoted by NX, okay? Open neighborhoods. Let Vx be a subset of U of X. We say that Vx is a fundamental system of neighborhoods of X when for all Ux in Ux, capital Ux, there exists some element of Vx such as Vx with this property, and we say Vx is a base for Ux, is a base for this Ux, okay. We say that Vx is a fundamental system of neighborhoods when we have this property. For each Ux in Ux there exists an element of Vx such as this with this property, and we have a very important definition: Hausdorff space. A topological space is called a Hausdorff space when distinct points can be separated by open sets in symbols for each X and Y in X with X not equal Y, distinct elements, distinct points. There exist two members of tau such that one of these elements contains X, another contains Y, and these two elements are disjoint. These two elements are disjoint, and Hausdorff spaces are very, very important topological spaces. Okay, so that if we consider a topological space such as this, for example, let this is our space. Okay, this is our space. Okay, this is our space. This space is called Hausdorff whenever if we consider any two distance points such as x and y, there exists two open sets such as u and v such that x belong to u, y belong to v, and these two open sets are disjunct, so that for each x and y in x, this is our topological space x. Okay, if x not equal to y, then there exists u and v in two with these properties. Three properties: x belong to u, y belong to v, and u intersect v equal to empty set. Okay, we say that this as a Hausdorff space. Hausdorff was a mathematician. Okay, an example of Hausdorff space is R with Euclidean topology. So that Euclidean topology is very, very important. R is Hausdorff because R with Euclidean topology is Hausdorff. Okay, because we don't have Hausdorff, this is H. Okay, Hausdorff, because for any two distance element in R, such as x and y, for example, x and y, we can consider this center And now consider two open cells such as this and this. These are V, for example, and these are U. You see that this U and V have this three property: is a member of U, Y is a member of V, and this U and V are disjunct. Now we see that we can specify this U and V exactly because this center point is x plus y divided by 2. Now we can consider a point before this and a point after this. For example, we can consider all of these. For example, we can consider U equal to x minus this and x plus this, because x plus this reach to this point, but this is an open interval and we consider as this y minus this and y plus this, okay, or any less than interval around x and y. For example, you can consider the center of these two, x plus y divided by 2 plus y divided by 2, okay, this is equal to x plus 2y divided by 4. And you can consider sorry 3y, okay, 3y. You can consider this as your v, y minus the and y plus this. And also the center of this x plus y divided by 2, and this is 3x plus y divided by 4, okay. And you can consider u x minus this 3x plus y divided by 4 and x plus this, okay. And many other u and v. We see that x belongs to this because x is the center of this interval and y belong to this, and these two are disjoint, so that we have this nice example. R with Euclidean topology is Hausdorff. And also you can another proofs. Let me define the definition of continuous function in the next session. Okay, I think it is enough for this session. I think that is Euclidean topology. Yes, Euclidean topology is very nice example. Do you have any questions, dear students? Do you have any questions? Okay, it is enough for this session. Thank you very much for your attention and see you later. Goodbye.